everyone, in this video we're going to go over chapter 2, functions. So this first section is 2.1, which is also functions. So function is a rule that describes how one quantity depends on another. So it assigns to each element x in a set exactly one element called f of x in a set B. So each member of the domain corresponds to exactly one member of the range. So we read this f parentheses x as f of x. So our f of x is the image of x under f, which is the range. Set A is called the domain, and then our range of f is f of x such that x is in A. So our independent variable is an arbitrary number in the domain of a function f. So our independent variable are like our x values. The dependent variable is a number in a range of f, and it's dependent because it's dependent on what the value of x is. So our input of x leads to our output of f of x. So here's two different diagrams of a set A and a set B. So in this first one, we'll label it 1. And this one 2. So in 1, we have our input going to output. So 1 goes to 20, 2 goes to 20, 3 goes to 30, and 4 goes to 40. So as we can see, each x is mapped to exactly one member of the range. So this first one is a function. However, the second one, 1 goes to 10, 2 goes to 20, and 2 goes to 30, 3 goes to 40, and 4 goes to 50. So as 2 goes to 20 and 2 goes to 30, that means that 2 does not correspond to exactly one member of the range. Therefore, 2 is not a function. So no two ordered pairs have the same input and different output in order for it to be a function. So here's an example. We have f of x equals x squared plus 4. So we're going to express how f acts on input x to produce output f of x. So we square input and then add 4 to get the output f of x. So we're going to evaluate f at 3, -2, and square root 5. So we just plug in 3 for every time we see an x. So f of 3 equals 3 squared plus 4, which is 13. F of -2 is -2 squared plus 4, which is 8. F of square root 5 is square root 5 squared plus 4 equals 9. And then we want to find the domain and range of f. So the domain, as you recall, is the set of possible inputs. So what values of x can we input into f of x equals x squared plus 4? Well, we could input all real numbers because there's not a specific one that wouldn't work or is invalid in this case. Our range are the possible outputs. So as x squared is always going to be greater than or equal to 0 because we're never going to get a negative number, because if we square a number, we're always going to get a positive. For all x and r, we have x squared plus 4 is always going to be greater than or equal to 4 because x squared, if the least amount x squared could be is 0. So we're going to always have a 0 plus 4. So therefore, f of x is always going to be greater than or equal to 4. So our y is y such that y is greater than or equal to 4. So our fx and y are interchangeable. They're the same thing. So our range is 4, including 4, to infinity. So evaluating a function. So let f of x equals x squared plus 3x plus 5, and we're going to evaluate this at f of 2, f of x plus 3, and f at negative x. So the shadows here are the places that I'm going to plug in each of these different x values. So f of 2, we plug in our 2. So we have 2 squared plus 3 times 2 plus 5 is 4 plus 6 plus 5, which is 15. And notice how this f of x plus 3, so this entire term here is like our x. We could call it, in this case, we'll just call it b. So we're plugging in the whole term b for our x. So we have f of x plus 3 squared plus 3x plus 3 plus 5. So we square that, and then we get x squared plus 9x plus 23. Our f of negative x, it's the same thing. So we're plugging in this whole term for our x. So notice how when we square it, we're squaring not only the x, but a negative x. And then plus 3 times negative x plus 5, we get x squared minus 3x plus 5. Okay, for our next example, we have fx equals 2x squared plus 3x minus 1. And we're going to evaluate this at f of a plus h minus f of a over h. So this is a common form in calculus, and it's typically known as the difference quotient. So we're going to go ahead and evaluate this. So I'm going to break it up piece by piece. So first I'm going to do f of a plus h first, and then simplify that. So I'm plugging in the whole a plus h into our x's. So I have 2a plus h squared plus 3 times a plus h minus 1. So I square that out. So I have 2 times a squared plus 2ah plus h squared plus 3a plus 3h minus 1. Simplify that. And we have 2a squared plus 4h plus 2h squared when we distribute, plus 3a plus 3h minus 1. Okay, now I'm going to find my f of a. I'm going to plug in the a for the x, so I get 2a squared plus 3a minus 1. And now I'm going to combine these two. So this is my f a plus h. This is my f of a. Okay, so I have my whole term. Don't forget this minus here is distributed to my whole f of a. So I distribute the minus. Okay, so we have 4ah plus 2h squared plus 3h over h. I could factor an h out, and then when I factor an h out, there's cancels one of those, cancels that one, cancels that. So I get 4a plus 2h plus 3. Okay, here's an example of a piecewise function. So a cell phone plan is $39 a month. So this plan has 2 gigabytes of free data and charges $15 per gigabyte for any additional data used. So monthly charges are a function of number of gigabytes used. So we have $39 a month. So that's our first thing. So if we don't use, so we have 2 gigabytes of free data. So unless we use 2 gigabytes or more than 2 gigabytes, then that's when we get charged. But if we don't, then it's still free, but we're charged a flat rate of $39. So our rate is $39 if our gigabytes is between 0 and 2, including 2. So additional data is the $39 flat fee plus 15 times x, which is the amount that we used in total, minus the 2, because the 2 is representing the 2 gigabytes of free data. So if x is greater than 2, that's our piecewise. So then we're going to find our c at 0.5, c at 2, and c at 4. So as 0.05, oh, that was supposed to be 0.05. So at 0.05, that's less than or equal to 2. So we're using this one here. So we'll call that 1, that one 2. So we're using 1. So that's 39. 2, c at 2, that's less than or equal to 2. So we're also using 1, so that's 39. All right, so we have 4 is greater than 2, so we're going to use the second function here. So c at 4 is 39 plus 15 times 4 minus 2, which is 69. Okay. So net change is the value of a function f as input changes from a to b, where a is less than or equal to b is f of b minus f of a. So for example, f of x equals x squared, so our net change from 1 to 3 is f of 3 minus f of 1 is 8. Okay. Just review. So our domain of a function is the set of all inputs for the function. So sometimes the domain is stated explicitly, such as f of x equals x squared, where 0 is less than or equal to x, and then x is less than or equal to 5. So that's explicit domain. But sometimes our domain isn't explicitly stated and we have to find it ourselves. So like for f of x of 1 over x minus 4, it's not defined at 4, so x cannot equal 4, and gx equals the square root of x. G isn't defined for negative x, so x has to be greater than or equal to 0. So here's some examples. We have to find the domain of 1 over x squared minus x. We factor, so we have 1 over x and then x minus 1. So when is our denominator going to be equal to 0? Well, that's when x equals 0 or x equals 1. So x can't equal 0 and x can't equal 1. So this is our set builder notation, and then this is our interval notation. So these are valid inputs. Okay, so g of x equals square root 9 minus x squared. So our 9 minus x squared has to be greater than or equal to 0. So we have it split up, and we have negative 3 is less than or equal to x, less than or equal to 3. And then if you need review, we have that in section 1.8. So our h of t equals t over square root t plus 1. So we have t plus 1 has to be greater than 0, so our t has to be greater than negative 1. So because if it was negative 1, then our denominator would be 0. So t is greater than negative 1, and then this is our integer, or not integer, interval notation. So there's 4 ways to represent a function that we've gone over so far. So we could represent a function verbally using descriptions, algebraically using a formula, visually with a graph, and numerically with a table of values. So here we have an example of the different ways we could represent functions. So we have f of c is the Fahrenheit temperature corresponding to Celsius temperature C. So verbally, our function would be to convert from C to F, we multiply C by 9 over 5 and add 32. So algebraically, this function would be f of c equals 9/5 c plus 32. Numerically is when we would make our table of values and we had our different c's, and then when we plug them into our f of c, we have our Fahrenheit, and then visually is the graph, where we plot our values from the table and then we look at what the relationship is and the line. Alright, I'm going to go ahead and stop the video and then we'll continue with chapter 2.2, graphs of functions.